to the simplest explanation to Heisenberg's uncertainty principle demonstration, which is given by Dr. Derek Muller of Veritasium Channel. I think that it is one of the best demonstrations in which I understood Heisenberg's uncertainty principle well. So I'm going to make it more simple to grade 11 and 12 students with the help of vector addition and subtraction. So I urge my viewers that before seeing this video, you just go to YouTube and type Heisenberg's uncertainty principle by Veritasium. Then you will get one of the very good feeling and demonstration given by him. But still I want to simplify it further in form of the vector equations. So here are the slits, and the slit is along x-axis. So slit is just an opening through which the light can enter, and this is the screen. So from here the light is going to go, that means the photons are going to go, and then the photons are going to pass through the slit, and finally they are going to fall on the screen. In A situation, the slit is kept very wide, so the width of the slit is very large, and here the width of the slit is kept very, very small. So what happens is, now if I assume a single photon going in this direction, suppose this is a single photon and this photon is going in this direction, and I am considering this line of motion of photon as y-axis and this as the x-axis. Same situation would be seen over here, photon moving in a straight line. So its initial momentum pi, here also its initial momentum is pi. Now we can see that the momentum is purely along y-axis. So pix is 0, pix is 0, because the vector itself is on y-axis, right? Now when this photon reaches over here, this photon can be found between a huge gap because the slit is kept very wide. So this photon can be found between these two places anywhere. So compared to the size of the photon, the uncertainty in the position is very large, because I am saying that the photon can be found between these two places anywhere, and the slit is actually very wide open. So uncertainty in position along x-axis is too large. So that means delta x itself is very large, right? So in this situation, delta x is very large. Now when this photon reaches over here, the photon can be found between these two places. So along x-axis, the position of the photon can be anywhere. So now the error or the uncertainty in the position is very, very small, because I may be able to give you almost correct position of the photon over here, whereas over here I won't be able to give you the correct position of the photon along x-axis. So improper position means large error means more uncertainty. So here delta x would be comparatively smaller, right? Now what is Heisenberg's uncertainty principle? So it is delta x into delta px, that is equal to h upon 4 pi. Now when we are applying this Heisenberg's uncertainty principle, make sure that we are applying in x or in y direction. Now what happens is, since delta x is very, very large, delta px has to be very, very small. So I am going to consider this as almost 0, so that you can understand it in a better way. Now if the photon after passing through the slit continues to move in a straight line, then the final momentum pf is also along y-axis. So again the final pfx is again 0. So that means before passing through the slit and after passing through the slit, the change in momentum along x direction is 0. It is because delta x is too large, so delta px should be very, very small. Now on the other hand, over here what happens is, this photon should move in this direction and it should hit the screen somewhere over here. And why it is so? Because the final momentum pf is like this. Now if pf is like this, then I will get some component I will get some component pfx in x direction. So earlier it was 0, now it is not 0. So I am getting some value of delta p x as something, and now it is greater compared to over here. So if you try to reduce delta x, delta px has to increase, and in order to increase delta px, the photon has to van out in these directions. The photon can also travel in this direction like pf, then and only then there will be some momentum along x-axis, and then momentum before and momentum after passing through the slits along x direction, there will be some difference noticed. So if you are decreasing delta x, delta px must go high, and delta px must only go high. They will only go high if the beam of photons, if they fan out in both the directions, because they have to keep up the Heisenberg's uncertainty principle. So here delta x is very large, so delta px is almost 0. So that's why the photon will hit the center of the screen. They will move straight. But if you actually decrease the width of the slit, so you are actually decreasing delta x. So for that, the delta px has to increase. For increasing delta px, the beam has to fan out, or the photon has to travel in slant directions in order to keep up the Heisenberg's uncertainty principle. So guys, hopefully you have enjoyed the explanation, and if you have still not subscribed the channel, then please do that, and thank you for watching the video. Thank you.